Good evening, everyone. Welcome to week 5 problem solving sessions on the essentials of data science with R software. I am Shreya, one of the TAs for this course, and today I'll be discussing some concepts and solutions of the problems that were discussed during week 5 lectures. But before moving on, is there anything that you would like me to answer? Any doubts or any comment in general which you want to be covered? Please let me know. Okay, then if nothing, I am going to proceed as I have planned. Okay. So during week 4, I'll just pull up the slides. Is it visible? Okay. So during week 4 lectures, we learned how to actually draw a sample, and that could be SRSWR, that could be SRSWOR, and we also learned how to calculate or estimate population mean, population variance, with sample means, sample variance, and we also learned a term about which was called standard error for estimation of mean. Okay, so briefly in this week, in week 5, we are mostly going to cover how do we have a confidence interval for estimation of mean, and we would definitely need all the quantities that we discussed in the previous session. Okay, so I'll briefly write all of the formulas that we were using. So if we had a population where it was denoted by y1, y2, y capital N, sorry. So if these n were capital N population units, and from here we draw a sample of size n, so then y1, y2, yn are my observations, or this is actually my sample size. Now, population mean mu was 1 by n summation I equal to 1 to n capital YI. And population variance sigma square is actually, so this is denoted by y bar, and population variance sigma square is actually 1 by n summation I equal to 1 to n yi minus y bar whole square. On top of these, we also learned a term which is this one, capital S square. And how is this different from the population variance? This is almost the same, but the denominator is 1 by n minus 1 summation I equal to 1 to n capital yi minus y bar whole square. Okay, and what did we do? We estimated. So if this is the population over here, and if this is mu, we tried to estimate mu with sample mean, that is 1 by n small n summation I equal to 1 to n yi. Okay, and this was the expression irrespective of whether the sampling has been done with replacement or SRS WOR. Okay. And we also learned about the variance term. Now, just excuse me for a minute, I'll just have some water. Sorry about that. So where was I? Yes. So this is the estimate of the population mean, which is calculated with the help of the sample mean. And we also learned that this variation of, so mu hat, I could also call it as y bar. Okay, so variance of y bar, if the sampling is with replacement, this was actually n minus 1 by capital NN S square. And if the sampling technique is without replacement, this was actually capital N minus N by nn into s square. Okay, and since this is also a population parameter, this capital S square, if we really wanted the estimate of the variance, then we would write y bar wr and put a hat over here. That would be n minus 1 by capital NN into small s square. And how is small s square defined? It is actually the counterpart of capital S square. So it would be 1 by n minus 1 summation I equal to 1 to n yi minus y bar whole square. Okay. So if we had this estimate y bar wr, this was actually, so for width replacement it was s square by n, and for without replacement this estimate turned out to be capital N minus n by nn into s square. Okay, so now the question becomes, how with these quantities can we estimate a confidence interval? So what is actually a confidence interval? Let me just give you a brief idea. So if I say that probability, this population parameter lies between A and B, this is equal to 0.95, then AB is the 95% confidence interval for mu. So what I am essentially trying to say is that mu is contained in this interval with a probability of 95%. So now the question is, why will we do this? So previously what we were doing with the help of y bar, this was actually giving us a point estimate. Okay, so if let's say the, excuse me, sorry, if let's say the population parameter for some things, let's say height of an average Indian female, so if I say the true height is actually something around 165 centimeter or something like that. Okay, so if I had the capability to sample all, like from census data, and then calculate this mu capital Y bar, then I could have determined that this is the population level parameter. Now, but since I am not doing a census, this quantity is actually unknown. What I am doing is I am collecting a smaller subset which is very similar to population, and from here I am trying to get mu hat. Okay, so if I give y bar based on my sample, let's say 161 to 170, some random numbers, let's say I collect 100 samples all between this range, and then I do a mean. Okay, So that would actually give me a single quantity, which is like the point estimate. So I could get something like 164.5, I could get something like 166.7, I could even get something way off 170.5. Okay, so that will depend on the kind of sample I'm getting, and associated with mu hat I'm going to get a standard error. Okay, which would tell me how the standard error is actually will quantify the amount of variation around the original mu that was there. So if we have lower standard errors, it simply means that we have estimated with greater proportion. But apart from mu and standard error, I have no way to say how confident I am with this result. Okay, but if I provide a confidence interval that falls under the purview of interval estimation. So this actually provides a little bit more flexibility, and it also provides a confidence to our claims. So if I'm able to say that okay, my mu is actually less than or equal to 1, it could fall between 160 to 164, and I am 95% confident that this is going to happen. So what I'm essentially trying to say is that the population parameter could that I am this percentage confident that the population parameter will lie between the lower bound and upper bound of my confidence interval. So the goal here is actually to get a narrow confidence interval. Okay, just imagine if you say probability, I am 95% confident that this will lie between 160 and 164. Okay, and somebody could even say that I am 100% confident that this height will be greater than 0 and will be less than 500 something centimeters. So even if I have high confidence here, I am not going to support this person. I would rather believe this person, because this is actually a given thing. I have a huge range of uh, possible or viable options for mu, and it is possible that it can belong to, or it belongs to this region. So it would actually imply that mu can have a large variation, but I don't want that. I just want my estimate, or uh, the whatever interval that I'm proposing, to be as close to mu as possible. So if I want to have a good estimation, I should essentially have a narrower confidence interval. uh, does this make sense? Am I making sense? Okay, hopefully. So so in the context of confidence intervals, what do we write and what do we not write when I am talking about some sort of sampling techniques? Okay, so if, let's say, the question is I want a confidence, let's say I would write it like this: if I want an 1 minus alpha percentage confidence interval for capital Y bar, okay, mu. Then how should my this capital Y bar look like, this confidence interval look like? It should be Y bar, and let's say the population variance. So this term will vary depending on whether population variance is known or unknown. Okay, so capital sigma square, let us first assume it's known. So then 1 minus alpha % confidence interval for Y bar would actually be Y bar, sample Y bar minus, so this is actually Z alpha by 2 is the upper alpha point of a normal 0-1 distribution, root over variance of Y bar, and again Y bar plus Z alpha by 2 root over variance of Y bar. Now what is this Z alpha by 2 term? So if this is how a normal distribution looks like, here I have the center, okay, this is 0. So normal distribution, you know, is actually a bell-shaped curve, and let's say this is the mean of the distribution. Z alpha by 2 is actually that point on the x-axis, okay. I would call this Z alpha by 2. If I draw a line here at x equal to Z alpha by 2, then this area that I'm going to have on the right side, okay, this area, this much area is actually alpha by 2. Okay, and since this distribution is symmetric, I am going to have, if I call this position Z 1 minus alpha by 2, then if I draw a line over here, then it means that area above this particular line is actually 1 minus alpha by 2, or in a reverse manner if we say, then the area below this part is actually 1 minus alpha by 2. Oh, sorry, this area is, this area is actually alpha by 2, because any alpha point is that point on the distribution such that the, if I call it an upper alpha point, then that is the point above which the area is whatever here I am reporting as, okay. And since this is a symmetric distribution for normal 0-1, I would have Z alpha by 2, and Z1 minus alpha by 2 would be actually minus Z alpha by 2, because it is symmetric with respect to 0. Okay, this only works for a normal distribution, and or I would say this would work that upper alpha point is equal to or lower alpha point is equal to minus upper alpha point. This will only work if the distribution is symmetric. Okay. So now coming back to this question. So here, for any population parameter, population mean y bar, this is actually how my confidence interval is going to look like if sigma square or the population variance is known. Okay, but if the population variance is unknown, then how will it look like? So if it is unknown, one minus alpha % confidence interval for capital Y bar will look like this. This will be Y bar. Instead of the normal 0-1 distribution, we'll have a t distribution. This is some other distribution. Okay, where this is also a t distribution, which is also a symmetric distribution about 0, and t alpha by 2 is this point, such that if I draw a line x equal to t alpha by 2, then this area, the area above this line, is actually going to be, this area is alpha by 2. Okay, now this one, how do I calculate in R? Okay, so let me move on to my R console. Just a second. Okay, is my screen visible? No, I have not shared. I hope it's visible now. Okay, so how do we calculate these sort of things using the software? Now, to demonstrate, first let us have some samples. So let's say I have sample with replacement okay, let me have a sample with replacement and another sample without replacement. So I'll take this example of height. So I could have, let's say, by some means I know that the lowest possible height could be something around 150 centimeter and the highest possible height would be something around 180 centimeter. Okay, so this is my population. So I have, it could be any of these measures. Okay, or it's better not to write this way because height is actually a continuous variable. Okay, but for the purpose of illustration I'll keep it this way because I think it will be easier. Okay, so sample with replacement and sample without replacement. How am I going to do that? First, if I want my calculations to remain same every time I run it, I'm going to set a seed. So I will write set.seed some random number. Okay, and I write sample x. So I'm sampling from height, and let's say I sample 15 individuals. Okay, and since it is by default it's without replacement, I have to add replace equal to true. And similarly I will have sample height size equal to 15 replace equal to false. Let me just run everything all together. Okay, so I have my sample with replacement. It looks like this. So here you see 155 is repeated twice. 150 is also repeated twice. The others seem to be pretty distinct. And sample WOR, all of them are distinct. Now if I want Y bar WR, I am going to write mean of sample WR. Okay, and Y bar WOR is actually mean of sample WOR. Okay, so this is actually Y bar WR. (161.733). Here you can see, and this is mean of sample WOR. So okay, so this is actually 165.2. Okay, so I got the means for both the samples. Now how do I get the variance? So in order to do that, I will first want the variance of y. This actually is my small s square. Okay, if you, so I should write sample WR. This is actually small s square, whatever I'm getting. Sample WOR. This is 66 and this is 72.31429. Okay, now if I have to get the 95% confidence interval, then variance of sample without replacement is actually, so if I can go back here, so the estimate for y bar WR is s square by n, and variance of y bar WOR is n minus n capital N into s square. So if I consider the WOR case, let's say, okay, so if I am considering the WOR phase, then, and the thing is sigma square or population variance is known. Okay, then this one, the term hat of y bar WOR is actually n minus n by n into n this quantity into small s square, which is variance of sample WR. Okay, and what is the value of capital N and N? So capital N is actually how many elements are there in the population. So it would be length of height. If I give here, then I'll get 31. Okay, so there are 31 elements in this array. So capital N is 31. And small n is actually 15, whatever is the size of the sample. So if this is this, then how much does this come to? This is actually variance hat y bar WOR. Okay, so this is the quantity. Now what is the lower limit and what is the upper limit? Here population variance sigma square is known, so we have to get the square root of this thing. Okay, so if this is a term I say as v, then my lower limit will be actually y bar WOR minus z alpha by 2 into SQRT V. Okay, and my upper limit will be the same thing but plus. Okay, now how do I get Z alpha by 2? So Z alpha by 2 is actually that point on my normal distribution such that the area above is alpha by 2. So here if I say alpha is actually 5, so it would be 0.05, because I am actually curious in 1 minus alpha percentage. So if alpha is 0.05, then I would actually estimate a 95% confidence interval. Okay, so Z alpha by 2 is actually that point such that area above this point is alpha by 2, that is 0.025. So how do we calculate this? This is actually calculated by this quantile function called Q norm. Okay, Q norm actually gives me that point below which this P, so the Q norm, if by default if I have here, is actually providing me that point below which the area is P, because the default value is lower dot tail equal to true. So I could actually write Q norm 975, because alpha by 2 is in that case 0.025. Okay, so I could write Q norm 0.975, that will just serve my purpose. Okay, another way to write this, and it's the same thing, if you give Q norm this, it will come to something close to 1.96. okay, just remember this value Z alpha by 2 is actually a that is actually close to 1.96, given alpha is 0.05. that is important, not for all alpha. Okay, or apart from this, if you do not want to make this remember this, so you could also actually write 0.025, but mind you, in this case you have to specify lower dot tail equal to false. So then this will give me that point above which the area is this thing. So you see, it is also going to report 1.95. But had I not given this one, it would have given me minus 1.96. Because it's symmetric, it would have given me this thing. So if I am using the alpha by 2 parameter over here, I should always specify lower dot tail equal to false. Okay, and now I have the lower limit and I have the upper limit. So then lower limit is, if I write paste 95% confidence interval for capital Y bar is lower limit, comma, upper limit. I'm just concatenating with this paste command. Okay, and this is it. So see, here you would get what is the lower limit and what is the upper limit. So based on this sample, I can say that the population mean or average height of the population could be contained in this interval with 95% probability. That is all I'm saying. It could fall anywhere outside as well, but that chance of error is actually 5% because I am 95% confident that the Y bar is going to fall between these two ranges. Okay, now this was the case if, so currently let's say I am working with SRS WOR. So if this was the case if sigma square is known. Now let's say I have the same thing, but here sigma square is unknown. What is going to change? Well, this V is not going to change because that is the estimate of the variance. Sorry, it should be WOR. Okay, alpha is not going to change. Lower limit, upper limit formula also won't change. What is going to change is this part. So instead of getting the upper alpha point of a normal distribution, this is upper 0.025 point of normal 0, 1. I am going to get the upper alpha point for a capital T with n-1 df T distribution with df n-1. Okay, so T distribution is a symmetric distribution which is characterized by its degrees of freedom. So df stands for degrees of freedom, and for this particular case the degrees of freedom of the T distribution that we are considering is actually 1 less than the sample size. Okay, so if I have to do this, there I wrote Q norm. So here I am going to write Z alpha by 2 as QT. Okay, and here if I write QT, I have to specify the probability. So let me just write 0.975. What I am saying is that area, so I am not going to write lower dot tail equal to false by default if I keep it, and then I have to specify df equal to n-1. What would this imply? This would imply that give me the point below which the area is 0.975. because default is lower dot trail equal to 2. Or if I have to write it alternatively, I could just give this is 0.025 df equal to n minus 1, and then I must specify lower dot tail equal to false, because this z alpha by 2 is actually the upper alpha point. So you see this one is 2.144, same as this one. It's the same thing. So now the lower limit and upper limit is going to change, and I'm going to have this. So let's say sig known, and this was sigma known. Okay, so this one was actually when sigma known or sigma square known, it's the same thing. Okay, and here this would be sigma square unknown, and this, let me write sig unknown. Then this one will be so in this case, when sigma is not known, this is the confidence interval. So just note here, this might be true, this might not be true, but for all cases, but for this particular case, I see when sigma square is actually known, the interval is narrower. But when it is not known, the interval is a little broader. Okay, so this difference is visible over here. Oftentimes it's very less in magnitude, and we'll have to see how things go. But usually, since here when sigma square is known, I'm not estimating sigma square, I'm just putting that value. Okay, but when this is not known, I'm also estimating, I'm adding a layer of estimation, so my interval is becoming a little broader. Okay, so this was SR 95% confidence interval. If I do a simple random sampling, that is without replacement, and when sigma square is known or not known. Okay, now what happens if I perform an SRSWR and the conditions remain this: sigma square is known. Okay, so if sigma square is known, then this one, my V, actually becomes variance of sample WR, that is small s square by n, this one divided by small n. Okay, and since population variance is known, I am going to have Z alpha by 2 as this thing. Okay, and lower limit would be lower limit sig known y bar WR plus, okay, let me also write this as VWR square root of VWR, this thing. Okay, so lower limit when sigma known is y bar WR minus Z alpha by 2 into square root of VWR, where VWR is variance of sample with replacement by small n. Okay, and just let me write this down. So this will be WR, lower limit sig known WR okay, so if I just run this, how much do I get? Okay, this is the y bar WR confidence interval when sigma is known, and when sigma is not known, then this remains same. Okay, VWR remains same, lower limit upper limit also remains same. The only thing that changes is actually from a normal distribution it becomes a t distribution. So we should actually write so instead of Z alpha by 2, I think it would be better if I write T alpha by 2. Okay, so this would be T alpha by 2 and this also would be T alpha by 2. Okay, so this is how we should get this. So without replacement, sigma square unknown. So here it was sigma square known, and sigma square unknown is lower limit unknown WR and upper limit unknown WR. Oh, okay. Alright, so I'll just rename here so that it's easier later. Z alpha by 2, lower limit sigma known WOR, and this is WOR, Z alpha by 2 square root of VWOR. Okay, Y bar, this is WOR, sigma square known, this would be WOR, and this would also be WOR. Then I have variance unknown, so here also it should be VWOR, and here instead of Z I should have T because it's sampling from a QT in -1 distribution. WOR, sigma square unknown. Okay, and with SRSWR this is the thing. Okay, so if I just clear this and run all of this together, and then if I just combine the paste lines and then try to write it, so this is without replacement sigma square known, this is without replacement sigma square unknown, this is with replacement sigma square known, and this is with replacement sigma square unknown. So in both the cases you will see that whenever sigma square is unknown, the confidence interval is becoming a little broader. Okay. And this actually change is happening whether we have a Z distribution or a T distribution, and you could look up and check whether which one is more or which one is less and things like that, that is causing this thing. Okay, right, so this is how you are going to calculate 95% confidence intervals based on the sampling technique. Okay, and also on the confidence interval. So let's say you have the same can you see my slide? 1 second. Okay, coming back here, if let's say I have this as my question, okay, so a researcher is conducting a study on the amount of time employees in a company spend on personal phones, and the distribution is skewed. A random sample of 60 employees is selected, following data is obtained: sample mean, sample standard deviation. So this is actually square root of S square, and this is y bar, small y bar. Given that the researcher is still interested in calculating 95% CI. Okay, so just imagine for this for the time being, don't consider these lines. Let's say, suppose let us assume everything is normal and things like that. So a random sample actually means sample with replacement. Okay. The researcher, let's say, is interested in calculating. I suppose, let's say I change it. I make it 99% confidence interval for the average time employees spend. Okay. Now, since I have already mentioned here that this is a random sample of 60 employees, random sample is usually would mean with replacement sampling. Okay, so if I have this, then a 99% confidence interval for me would be y bar minus sample standard deviation is given. So sigma square here was unknown, let's say. Okay, so here I have information on small s square. So then this would be actually t n minus 1 s square by n root, and again y bar plus t n minus 1 root over s square by n. Okay, so here what should I give? Here y bar, y bar is given 45, s square is given, n is given, n is equal to 60. So all I need is tn minus 1. Okay, so here since I want a 99% confidence interval, I should give qt 0.9 95. So it would be 0.01 by 2, so 0.005, so it would be 0.995, and n minus 1 is 59. Either this, or I should give qt 0.005 59 lower dot tail equal to false. We'll land up at the same thing. So let us check this out. So here I wanted a 99% confidence interval. So here I'm going to write qt 0.995, df would be 59, this is 2.66, or 0.005 59 lower dot tail equal to true. So sorry, lower dot tail equal to false. So it was actually the same thing, 2.66. Okay, so 2-3 key points that we should take into consideration while solving such kind of problems is that what is the percentage of confidence we need? If it is 95%, if it is 90%, if it is 99%, so corresponding alphas will be 0.05, 0.1 and 0.01. Similarly, we'll have alpha by 2, 0.025, 0.05, 0.005. Okay, and accordingly we'll have to place this alpha by 2 in whether a q norm or a qt depends, this one when sigma square is known, and this one when sigma square is unknown. Okay, and the sampling scheme, if I have with replacement, then s square by n will be my variance hat y bar, and if I have without replacement, variance hat y bar will be capital N minus n by nn s square. Okay, so these are the prime considerations while calculating a 95% confidence interval. Similarly, let's check out the next one. So here again, let me show an example with 90. Okay, so a researcher is conducting a study on the number of hours worked per week by employees at a company. Total population of employees is n equal to 200. So capital N is equal to 200, and the researcher decides to select a sample of 15 employees using SRSWR. So small n equal to 15. Estimate the population mean number of hours worked per week. Okay, so whatever I have, let's say y bar. Okay, so this is actually mean of y. Done. And now okay, so this is the mean of y. Calculate the standard error of sample mean. So standard error of sample mean is actually variance of y hat square root. So this will be square root of n minus n by capital N n s square. Okay, s square, how will I get? S square I'll get with variance of y. Alright, and construct a 95% confidence interval for the population mean. So a 95% confidence interval in that case would be y bar minus t n minus 1 alpha by 2. So here I'm trying to find out a, let's say, 90%. So this would be 0. This would be 0.05 root over n minus n by n n s square, and y bar plus t n minus 1 0.05 root over n minus n by capital N n s square. This is the confidence interval that I'm going to get. So let me just find out this, how to do this. So same thing, qt 0.05 and then small n minus 1. So I have done 15 samples, so it would be 14, and I should definitely specify lower dot tail equal to false. So this comes to 1.76, and I'm going to plug in that value, calculate, and then I'm going to get the 90% confidence interval. So this actually is giving me 90% CI for capital Y bar or the population mean. Is it clear? Any questions, comments, doubts, anything? So this was an estimate of population means. Whenever I would like an estimate of population total, y equal to summation y, or yes, y equal to summation yi or n y bar. Okay, so then y hat is actually capital N into small y bar. Okay, and variance of y hat is actually then n square into variance of y bar. Okay, and this becomes n square into n minus n by n s square in the case of WOR, and n minus n square n minus 1 by nn capital S square in WR case. And if I want an estimate of the variance, so variance y hat is actually then n square n minus n by capital Nn small s square, and in this case it is n square capital S square by n. This is for WR and this is for WOR. All right, so next what we learnt is actually estimation of proportions. Okay, so questions like what percentage of the society is vegetarian, let's say, or something like this. What percentage of the society is obese? So these are actually questions where we ask a person. So if this is a person and we ask obese, they say yes or no. We ask or we measure anything. Okay, we measure BMI, let's say, body mass index, and then conclude if somebody has obesity or not. And then from the sample we try to estimate what proportion of the population is actually suffering from obesity. All right, so in order to do that, how do we proceed? So let's say I have a population, total number of units is actually n. Okay, So this is my population. Out of which I have something like this, some white boxes, some black boxes. So let's say the black box is case or person who have responded yes, who do have obesity, so the actually obese ones. And we also have the white ones, which are I would call control, but actually they are not obese. Okay, so just some, so let's say here if I have C obese people, then I would have N minus C non-obese people. So then P, capital P, probability of obesity as per the frequency definition would be capital C by N. And capital Q, if I say probability of non-obesity, is actually N minus C by capital N. And we'll see that capital P plus Q equals 1. Okay, so in these sort of scenarios also the estimation process is fairly straightforward. Okay, so what and how is these sort of proportions, population proportions, estimated? So this capital P is actually population proportion, right? So here this capital P hat is actually estimated by small p, which is number of cases small c by capital N minus small c. So if from that population I have a sample, so this is my sample, and I have small c cases and small n minus c controls. So then the sample proportion is a point estimate of population proportion. Okay, and Q hat is how much then? Q hat is also given by, small p is capital C by small n. Extremely sorry. Small p is the sample proportion, so it would be capital C by small n, and Q hat is actually small q, which is n minus C by n. And you will note that this small p plus small q also equals 1. Okay, so given this, how do we find out the variance, or rather the standard error of estimation of this this population parameter, which is actually nothing but the proportion. Okay, so here we say that if you remember, this is yes or no question. So similarly, if I define a function where yi equal to 1 if obese and 0 if not, then summation yi I equal to 1 to n is actually going to give me capital C, right? And summation and yi if sample I is obese or not, 0 if not, then again summation small yi I equal to 1 to n is actually going to give me the small number of cases. Okay, and now let us write summation capital I square this is also going to give me capital C. Okay, or I could also write this as capital N into P, because capital P is C by N, right? So then the variance expression, that is capital S square, that becomes 1 by n minus 1 summation I equal to 1 to n yi minus y bar whole square. So this is 1 by n minus 1 summation yi square minus n y bar square. Okay, so this I actually can write as n into p minus n into p square. So then this becomes np 1 minus p by n minus 1 or npq by n minus 1. Okay, so then the estimate of this capital S square is actually given by small s square, and that is nothing but 1 by n minus small n minus 1 summation yi minus y bar whole square I equal to 1 to n, which is 1 by small n minus 1 summation yi square minus n y bar square. This is 1 by n minus 1 summation yi square small yi square is also going to give me the number of cases C, or I could write it as n into small p minus n into small p square. So this would be n by n minus 1 pq. Okay, so even for proportions, if I have to find a confidence interval for proportions, then I should have y bar minus let's say sigma square is known or sigma square is unknown, something like this. So given on the status of sigma square, it will be y bar minus some distributional cutoff point, and then it would be square root of the variance of y bar. Okay, and variance of y bar would be given by if it is with replacement or if it is without replacement accordingly, with the help of this small s square formula. Is that okay? Now oh, you are writing anything, your board is not visible. Oh, I'm extremely sorry, extremely sorry. I forgot to change this. Thank you, ma'am, for letting me know. So I was here. Are you able to see now? I'm not able to hear you.
Now it's visible, ma'am.
Okay, ma'am. All right. So yes, so if I was talking about estimation of population proportion. So if I have capital N number of population units, and among which I call that the black boxes are actually cases, people who are actually obese, and the white ones I call them as controls because they are not obese. Okay, I would get this number P and Q if I could sample, or if I could enumerate each of the individuals in the population and ask, are you obese, or measure them, some obesity determining factor. And then if I see yes, if they say yes, or if they truly turn out medically obese, I categorize them into cases, and if not, I categorize them into controls. So let's say I have capital N number of individuals, and I find that out of which capital C are actually obese, and likewise capital N minus C are not obese. So then my probability of obesity, the population probability, true population probability, had I been able to ask each and every individual, it would have been capital C by capital N. And then this probability that a person is not obese, that proportion would have been capital N minus C by capital N. Now here, from this population, if I sample an n number of individuals, smaller number of individuals, then this small, and if out of these small n, let's say C number of people are cases and n minus C number of people are controls, then small p would be my sample proportion, and that would be small p by small c by small n. And this sample proportion would be an estimate of the true actual population proportion. And consequently, small q, which is the proportion of non-obese person in our sample, that is small n minus c by small n, that would be an estimate of the population proportion of non-obese people. So in both the cases, both these probabilities or proportions add up to 1. Now, population mean is estimated with population with this parameter, let's say small, with the sample proportion. Now, how do I get the standard error of this? So in order to get standard error, I would need the small s square quantity. So how do I get that? So if I consider the population scenario, let's say here, and I categorize every individual into obese or non-obese, then if I take a sum of all yi's, I would get the total count of obese people in the population. And here I am writing the sample counterpart. Then if I take a sum of small yi, then I would also get the number of people in the sample who are actually obese. Similarly, if I quantify this term, summation yi square, this would also be 1 only if the ith person is actually obese. So summation yi square is also actually capital C. I could write this as capital N into P, since P is C by N. Okay, and then if I try to write down this formula of capital S square, then I find that this can be expanded in this manner, I equal to 1 to capital N, and this term is actually NP and y bar is capital P. So NP minus NP square, I would have NPQ by N minus 1. And these terms would accordingly be so capital S square will be estimated by small s square. So small s square in that case also turns out by as small n by n minus 1 PQ. Now based on the sampling technique, if it is with replacement or without replacement, we would have, so if it is SRSWR, we would have the variance of if it is SRSWR, we would have the variance of y bar is actually P, WR would be n minus 1 by n s square, and variance of PWOR would be n minus n by n capital S square. Okay, and this quantity will actually be, so I should not write capital P, so it would be variance of small p, because small p is here my y bar. Okay, and capital P is capital Y bar. Okay, so this quantity is actually n minus 1 by nn into whatever we wrote, n pq by n minus 1. So this would be pq by small n, and here it also will be n minus n into n pq by nn n minus 1. So this would be n minus n by n minus 1 pq. And if we want to estimate, their respective estimates would be, so if I go variance of small p, wr hat will actually be small p small q by small n, and variance hat pwor would be capital N minus 1 by n minus 1 into small p small q. Okay, and I was also talking about estimation of population total. So far with proportions, or normally we were estimating the population mean. Now if we want to estimate the population total, then capital Y is actually summation I equal to 1 to capital N yi, that we can write as capital N into y bar. So y hat would be, if I write capital N into y bar hat, and that is capital N into small y bar, because estimate of population mean is sample mean. And mean of this thing, y total, so y total is this thing, and then variance of y total is actually n square into variance of y bar. So if I have let's say if I have k equal to a x or something like this, then variance of k is actually a square into variance of x. Okay, but if I have k equal to a plus x, then variance of k equal to variance of x. So if I have anything multiplied with my random variable, then variance of this new combination actually becomes whatever scalar quantity I have, that square into variance of the associated random quantity. Okay, so here again, since we have capital N into y bar, variance of y total will be capital N square variance of y bar. Okay, and then variance of y bar will be this or this, depending on whether we have WR or WR. And then if I want an estimate of the variance of y hat, then that is given by this term. Whatever variance of y bar estimate we had, that into capital N square. Okay, so this was all about week 5, and I hope you'll be able to solve the questions that are actually given. Yes.
Thank you, ma'am.
Yes,
Thank you
ma'am.
for your explanation.
Thank you, ma'am, for joining. Do you have any queries?
Ma'am, would I get a recorded session
Yes, of course. This session will be uploaded on YouTube.
when you are going to upload, ma'am?
I'm going to do it right away, so I think you'll
Hmm.
get it by tonight.
Would you provide link for me, ma'am?
Yes, actually, I'll show you something. Uh, can you see my window?
Yes, yes, ma'am.
Okay, ma'am. So if you go to this SWAM portal, below
Hmm.
here you'll have some a link called Problem Solving Session January 2025. So if you click
Okay, ma'am.
here, you'll have this recording link which will point to a Google Sheet, and
Okay,
here
thank you, ma'am. Hmm.
you will have the presentation folder where I'll upload all the slides, and here you will have
Oh,
all the week-wise links. So you could go and check them out.
okay, ma'am. Thank you so much.
Okay, ma'am. Thank you so much for joining. Have a good night. Bye bye.
Thank you. Bye, ma'am.